So welcome grade 8 students. Please go to www.cathomeschool.com. Okay. Then please enter the curriculum. Alright. Then enter the password. Okay. After that, let's go click for the science because we will continue our lesson about work and energy. Types we will tackle today about the types of energy and some practices about our subject. Okay, so uh, I have this. I have some videos here about the work example problems. I believe this will help you. Okay, let's all watch this video.
I'm going to show you some examples of how to solve problems involving work. Imagine a 4-kilogram trash can. The trash can is disgusting, so someone ties a string to it and pulls on the string with a force of 50 newtons. The force of kinetic friction on the trash can while it slides is 30 newtons. The trash can slides across the ground for a distance of 10 meters. Let's try to find the work done by each force on the trash can as it slides across the ground. To find the work done by each force, we should recall the formula definition of work. Work equals Fd cosine theta, where theta is the angle between the force doing the work and the direction the trash can is moving. There are 4 forces involved here: tension, the normal force, the gravitational force, and the force of kinetic friction. In finding the work done for all of these forces, the displacement is going to be 10 meters, but the value of the force and the angle between that force and the displacement is going to differ for each of the forces. For instance, to find the work done by the force of tension, we'll plug in the size of the tension, which is 50 newtons, the displacement is 10 meters, and since the tension force is pointed in the same direction as the displacement, the angle between the force of tension and the displacement is 0 degrees. And since cosine of 0 is 1, the work done by the tension force is 500 joules. To find the work done by friction, we'll plug in the size of the force of friction, which is 30 newtons. The displacement is still 10 meters, and since the force of friction points in the opposite direction as the displacement, the angle between the force of friction and the displacement is 180 degrees. Since cosine of 180 is negative 1, the work done by the force of friction is negative 300 joules. Now let's figure out the work done by the gravitational force. The force of gravity is mg, so the force of gravity is 4 kilograms times 9.8 meters per second squared, which is 39.2 newtons. The displacement is again 10 meters, but the angle between the gravitational force and the direction of the displacement is 90 degrees in this case. And since cosine of 90 is 0, the gravitational force does no work on this trash can. Similarly, if we were to find the work done by the normal force, the angle between the direction of the displacement and the normal force is 90 degrees, so the normal force also does no work on the trash can. This makes sense because forces that are perpendicular to the motion can never do any work on that object. So that's how you can find the work done by individual forces. And if we wanted to know the net work done on this trash can, we could just add up the work done by each individual force. So the net work is going to be 200 joules. Now that we know the net work done on the trash can, we can use the work energy principle to figure out the speed of the trash can after it slid the 10 meters. The work energy principle says that the net work done on an object is equal to the change in kinetic energy of that object. So 200 joules is going to equal the difference in kinetic energy. If we assume the trash can started at rest, which seems reasonable, the initial velocity is 0. So we can solve for the final speed of the trash can, which comes out to be 10 meters per second. This time, let's say you take the trash can and lift it upwards with a constant velocity for a distance of 2 meters. In order to lift the trash can up with a constant velocity, you need to push with a force equal to the weight of the trash can, which means you have to push upwards with a force of 39.2 newtons. So to find the work done by the force that you exert, the force is going to be 39.2 newtons, the displacement is going to be 2 meters, and the angle between the force and the displacement is going to be 0 degrees because the direction of the force that you exert is in the same direction as the displacement of the trash can. So the work that you've done in lifting up this 4-kilogram trash can is 78.4 joules. To find the work done by the force of gravity, we can use the force of gravity, which is again 39.2 newtons. The displacement is again 2 meters, but the angle between the direction of the displacement and the gravitational force is 180 degrees because the displacement points up and the gravitational force points down. So the work done by the gravitational force is negative 78.4 joules, which means the net work done on the trash can is 0. And that makes sense because since the trash can moved upwards with constant velocity, there was no change in the kinetic energy of this object.
Okay, so I have this another video about work and the work energy principle. Wait.
An object, you've got to exert a force on that object. The amount of energy transferred by a force is called the work done by that force. The formula to find the work done by a particular force on an object is W equals Fd cosine theta. W refers to the work done by the force F. In other words, W is telling you the amount of energy that the force F is giving to the object. F refers to the size of the particular force doing the work. D is the displacement of the object, how far it moved while the force was exerted on it. And the theta in cosine theta refers to the angle between the force doing the work and the displacement of the object. You might be wondering what this cosine theta is doing in here. This cosine theta is in this formula because the only part of the force that does work is the component that lies along the direction of the displacement. The component of the force that lies perpendicular to the direction of motion doesn't actually do any work. We notice a few things about this formula. The units for work are newtons times meters, which we call joules. Joules are the same unit that we measure energy in, which makes sense because work is telling you the amount of joules given to or taken away from an object or a system. If the value of the work done comes out to be positive for a particular force, it means that that force is trying to give the object energy. The work done by a force will be positive if that force or a component of that force points in the same direction as the displacement. And if the value of the work done comes out to be negative, it means that that force is trying to take away energy from the object. The work done by a force will be negative if that force or a component of that force points in the opposite direction as the displacement. If a force points in a direction that's perpendicular to the displacement, the work done by that force is 0, which means it's neither giving nor taking away energy from that object. Another way that the work done by a force could be 0 is if the object doesn't move, since the displacement would be 0. So the force you exert by holding a very heavy weight above your head does not do any work on the weight, since the weight is not moving. So this formula represents the definition of the work done by a particular force. But what if we wanted to know the net work or total work done on an object? We could just find the individual amounts of work done by each particular force and add them up. But there's actually a trick to figuring out the net work done on an object. To keep things simple, let's assume that all the forces already lie along the direction of the displacement. That way we can get rid of the cosine theta term. Since we're talking about the net work done on an object, I'm going to replace F with the net force on that object. Now, we know that the net force is always equal to the mass times the acceleration. So we can replace F net with m times a. So we find that the net work is equal to the mass times the acceleration times the displacement. I want to write this equation in terms of the velocities and not the acceleration times the displacement. So I'm going to ask that you recall a 1D kinematics equation that looked like this. The final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. In order to use this kinematic formula, we've got to assume that the acceleration is constant, which means we're assuming that the net force on this object is constant. Even though it seems like we're making a lot of assumptions here, getting rid of the cosine theta and assuming the forces are constant, none of those assumptions are actually required to derive the result we're going to attain. They just make this derivation a lot simpler. So looking at this kinematic formula, we see that it also has acceleration times displacement. So I'm just going to isolate the acceleration times the displacement on one side of the equation, and I get that A times D equals V final squared minus V initial squared divided by 2. Since this is what A times D equals, I can replace the A times D in my net work formula, and I find that the net work is equal to the mass times the quantity V final squared minus V initial squared divided by 2. If I multiply the terms in this expression, I get that the net work is equal to 1/2 mass times the final velocity squared minus 1/2 mass times the initial velocity squared. In other words, the net work or total work is equal to the difference between the final and initial values of 1/2 mv squared. This quantity 1/2 m times v squared is what we call the kinetic energy of the object. So you'll often hear that the net work done on an object is equal to the change in the kinetic energy of that object. And this expression is often called the work energy principle, since it relates the net work done on an object to the kinetic energy gained or lost by that object. If the net work done is positive, the kinetic energy is going to increase and the object's going to speed up. If the net work done on an object is negative, the kinetic energy of that object's going to decrease, which means it's going to slow down. And if the net work done on an object is 0, it means the kinetic energy of that object's going to stay the same, which means the object maintains a constant speed.
Okay, now let's talk about energy. So there are also types of energy. First is, so what does it mean to have energy? Well, think about how you feel when you wake up in the morning. If you have lots of energy, that probably means you feel awake, ready to go, and able to do what needs to be done during the day. If you have no energy, then you maybe not feel like getting out of the bed, moving around, or doing the things you need to do. Well, this definition of energy is an everyday one, not a scientific one. It actually has a lot in common with the more formal definition of energy. Specifically, energy is defined as the ability to do work, which, for biology purposes, can be thought of as the ability to cause some kind of change. Energy can take many different forms. For instance, we're all familiar with light, heat, and electrical energy. Here, we'll look at some types of energy that are particularly important in biological system, including kinetic energy, potential energy, and chemical energy. Energy is never lost, but it can be converted from one of these forms to another. So first, let's tackle about kinetic energy. Kinetic energy, when an object is in motion, there is energy associated with that object. Why should that be the case? Moving objects are capable of causing a change, or put differently, of doing work. For example, think of a wrecking ball. Even a slow-moving wrecking ball can do a lot of damage to another object, such an empty house. However, a wrecking ball that is not moving does not do any work. The energy associated with an object's motion is called kinetic energy. A speeding bullet, a walking person, and a electromagnetic radiation like light all have kinetic energy. Another example of kinetic energy is the energy associated with the constant, random bouncing of atoms or molecules. This is also called thermal energy. The greater the thermal energy, the greater the kinetic energy of atomic motion, and vice versa. The average thermal energy of a group of molecules is what we call temperature. And when thermal energy is being transferred between two objects, it's known as heat. Next type of energy, potential energy. So let's return to our wrecking ball example. The motionless wrecking ball doesn't have any kinetic energy. But what would happen if it were lifted 2 stories up with a crane and suspended above a car? In this case, the wrecking ball isn't moving, but there is, in fact, still energy associated with it. The energy of the suspended wrecking ball reflects its potential to do work. If the wrecking ball were released, it would do work by making a pancake of someone's poor car. And if the ball is heavier, the energy associated with it will be greater. This type of energy is known as potential energy, and it is the energy associated with an object because of its position or structure. For instance, the energy in the chemical bonds of molecule is related to the structure of the molecule and the position of its atom related to one another. Chemical energy, the energy stored in chemical bonds, is thus considered a form of potential energy. Some everyday examples of potential energy includes the energy of water held behind a dam or of a person about to skydive out of an airplane. So we also have energy conversions. An object's energy can be converted from one form to another. For instance, let's consider our favorite example, the wrecking ball. As the wrecking ball hangs motionless several stories up, it has no kinetic energy, but a lot of potential energy. Once it is released, its kinetic energy begins to increase because it builds speed due to gravity, while its potential energy begins to decrease because it is no longer as far from the ground. Just before it hits the ground, the ball has almost no potential energy and a lot of kinetic energy. The same kind of conversion are possible with chemical energy. And we see lots of examples of this in our day-to-day lives. For instance, octane, a hydrocarbon found in gasoline, has chemical energy. Due to its molecular structure, which is shown above, this energy can be released in a car engine when the gasoline combusts, producing high-temperature gases that moves the engine's pistons and ultimately propel the car forward. Part of the chemical energy is converted to the kinetic energy of the car, while part is converted to thermal energy as heat emitted from the engine. Energy can change forms in a similar way in a living organism. For instance, energy stored in bonds of the molecule can power the movement of a motor protein and its cargo along a microtubule track, or the construction of muscle cell to move a limb. So these are the types of kinetic energy. Types of energy. So I have this types of energy, but the forms. So we have so we tackle about the types of energy like thermal energy, radiant energy, chemical energy, nuclear energy, electrical energy, motion energy, sound energy, elastic energy, and gravitational energy. So we also have these types of energy like thermal energy. Thermal energy is created from the vibration of atoms and molecules within substances. The faster they move, the more energy they possess and the hotter they become. Thermal energy is called heat energy. So we discussed chemical energy. Let's go for nuclear energy. Nuclear energy is stored in the nucleus of atom. This energy is released when the nuclei are combined, fusion or split apart, fission. Nuclear power plants split the nuclei of uranium atoms to produce electricity. Next type is electrical energy. Electrical energy is the movement of electrons the tiny particles that make up atoms along the protons and neutrons. Electrons that move through a wire are called electricity. Lighting is another example of electrical energy. Next is radiant energy, also known as light energy or electromagnetic energy. Radiant energy is a type of kinetic energy that travels in waves. Examples includes the energy from the sun, X-rays, and radio waves. Next is the light energy. Light energy is a form of electromagnetic radiation. Light consists of photons, which are produced when objects' atoms heat up. Light travels in waves and it's the only form of energy visible to the human eye. Next is the motion energy or mechanical energy. Is the energy stored in objects. As objects move faster, more energy is stored. Example of motion energy includes wind, a flowing river, a moving car, or a person running. The sound energy. The sound energy is the movement of energy through substances. It moves in waves and is produced when a force makes an object or a substance vibrate. There is usually much less energy in sound than in other forms of energy. Elastic energy. So elastic energy is a form of potential energy which is stored in an elastic object, such as coiled spring or a stretched elastic band. Elastic objects store elastic energy when a force causes them to be stretched or squashed. Lastly, gravitational energy. Gravitational energy is the form of potential energy. It is energy associated with the gravity of gravitational force. In other words, the energy held by an object when it is in a high position compared to a lower position. So we also have the law conservation of energy. While it may sound complex, the first law of conservation of energy simply states that energy can never be created or destroyed, but it can be transformed from one type to another. So, here is it. The types of energy, thermal, this one. Okay. So, this is the end of our topic about the work and energy. I hope you learned something. Please study because I'll give you a activity this coming Thursday about the work and energy. Thank you.